Hello again. We're going to be looking at a typical RC circuit, and you've already used the formula for it, but I wanted to be able to show you and have you follow along as to how it's created. How did they get that? So we're going to be combining some of our calculus and differential equation knowledge with our physics knowledge to see if we can just follow along. This is a rather in-depth one, but I think you guys will be able to follow along. So this is our circuit. We have a voltage source, we have a switch, we have a resistor and a capacitor. And as you know, they have certain characteristics. We're going to be looking at a particular situation when we have first time equals 0. So we're just going to close the switch. And we assume at that point, of course, that there's no charge on the capacitor and no potential difference across it. The potential difference across the resistor is U, whatever that happens to be at that moment. So the initial maximum current through the circuit is going to be this one right here. And we'll be coming back to that soon. We're going to apply the Kirchhoff rules, or the loop rule in English. And when we do that, we discover this. Now that you've seen before, but we're going to be taking a few more steps so that we can create a differential equation that we can then solve and get the formula that we're used to. So let's take a look at that. The sum of the potential differences across the capacitor and resistor, as you recall, they're always constant. Sometimes this is written in a different way. Sometimes it'll be all three on the left and then it'll be equal to the 0, but don't get hung up on small details. Different books do it differently. So if you have a book that says it the other way, just accept it. You can always rewrite it yourself. I don't know that any one way is better than the other. So now when we have a potential difference across the capacitor and it finally gets up to U, then the potential difference across the resistor is going to be 0, and that's when the current will stop flowing. And at that point, we'll have a maximum value on the capacitor. In other words, we charged it up. When the capacitor's full, as it were, you can't squeeze any more marbles in there. Marbles being the charged particles. So when it's full, it just stops. Okay, and that's when we get our next situation. So we're going to take the situations that we know, and we're going to apply the loop rule again. In other words, we're multiplying. We first substitute in that, and then we're going to basically multiply by C. We'll do that in just a moment. I'm going to take away some of the things that are here now because I want some room on the screen. So we'll be working with this blue differential equation. And from here on, we're going to basically just be manipulating this around using different math rules that we've learned during the last 3 years. Now I colored some of these in amber just so that you can more easily see what manipulations we're doing. And at this point, once we've done that, we're using the Kirchhoff rules again. We're allowing this to be, we're saying, okay, when I is dq dt, we use the loop rules, we go do our run around the track, and that's when we find this one. In essence, we're just multiplying everything by C. That's what it boils down to. If you find this a little too fast, don't be afraid to just pause and write the things down, draw your little pictures, and let yourself become convinced that this is, in fact, true. All right, let's take the next step. Once we have this new equation, I'm going to rearrange it into something that we can more easily take the integral of. At this point, this would be kind of messy to do that with. So we'll rearrange it. like I did right here. You can see again, because I used the amber color, you can see where the things went. And then I'm going to rearrange it one more time, just put the left side on the right and vice versa. I prefer to have dt on the right hand side. All right, we're going to take the integral of this now, kind of a simple step, and at the same time I'm going to be pulling out the constant form, RC. It's actually 1 divided by RC. So I'll go ahead and do that now. And there you can see it. Really no different than when we take the volume of an integral that we wrapped around an axis. We like to pull out the pi or any other constant that happens to be there. All right, let's take the next one. Oh, managed to take too fast to move there. When we integrate, we need our little integration constant, just like when we integrated our first things in calculus. We would add a plus c. In this case, we'll call it k. Now, in order to find that, we need to look at our assumptions. We're saying at t equals 0, we have a situation, and at the same time we have the q equal to 0. And when you look at this, what happens when t is 0? Well, that's gone. And when the q is 0, well, that's gone. All that's left is that. So let's go ahead and substitute that in where k was. And there we go. And now we need to remember back, about 1,000 years when you were taking your logarithms, and we're looking at the e-based logarithms, and we're going to do that. So the rule I'm using was here in this purple. Again, if it's too fast, pause and see if you can work it out yourself to become convinced of this. Now, once we have that, you may remember that sometimes it's quite nice to use this neat little trick, where you can say, we have the ln on the left side here. If I treat this as the power of e, in other words, I'm taking the anti-log of it, then things can clean up quite nicely. So that's what I'm doing here. There we go. We took the anti-log of the left side and the right side, and then we get this. Now it's starting to look a little bit familiar. You've seen this used in the equations, but this might not quite look right to you, and with good reason. That's because we're going to take another step. And let's get that done. We're going to take this blue one here and we're going to rearrange it algebraically. If you don't follow it, just pause and work it out, because at this point, this is beginning algebra now. So there you go. In the yellow box is the equation that we are used to. It's been in our books, and the closest thing that they would show, at least in the textbook we're using, was a very simple arrangement of the circuit. They make a few explanations, and then they say, and use this to calculate it. Not very satisfactory. So now you know where the equation came from and basically how it's set up. So, all right, I'll see you next time.